Start your day with a smile because you are lucky to have seen a new day. Good morning to one and all present here. Good morning is not just to greeting, it signifies a hope that the beautiful morning will bring a smile on your face and happiness in your life. On behalf of PG and Research Department of Mathematics, DG Vaishnava College, I welcome all the CSIR aspirants. Prayer is talking to God Almighty, the creator of whole universe. So let's begin our session with the presence of God. Now, Tamutal Vaitu, followed by college prayer. This is C4 workshop, Chase, Crack, Conquer, CSIR Net, which will make the CSIR aspirants to go to the next level. Today, our resource person is Dr. N. Sridharan, retired professor and head, Department of Mathematics, Alagappa University, Correct. Now, I hand over the session to you, sir.
Sir, now open your PPT, sir.
அது கொஞ்சம் Csir போட்டாங்க.
Sir, now open your PPT, sir. PowerPoint presentation, sir. Your
Yes. SR.
sir. Sir, your screen visible, sir, but not PPT, sir. Sir,
Hello, can I start now? Sorry. Next, side show போட்டு பாப்பா.
நீங்க ஃபர்ஸ்ட் ஆடியோ கேட்டுக்கு முதல்ல பேசுங்க அவங்க வாய்ஸ் வந்தா
sir,
பேசுங்க.
audio
Okay.
visible, sir.
Sir, voice here.
Yes, sir.
Are
Yes,
you
sir.
able to hear my voice now?
Yes, sir. Voice.
Okay.
Yes, sir. Audible, sir. Now audible,
I'll
sir.
just
Sir,
start the
sir,
complex
make it,
analysis. Okay.
sir, make it slideshow, sir. On your PPT.
Hello?
Make it. Sir, make it a slideshow, sir. Slide view, sir.
Okay, okay. இதுப்பா next இதுப்பா இதா next. Okay. I will start the Taylor's theorem. The function f of x is analytic in a domain D, and A is a point in the domain.
Sir, sir, sorry, sir. Sir,
Hello?
sir, please change into slide view, sir. In your
One
PPT.
minute.
Slide view, sir.
Side big பண்ணுமாப்பா side sheet
Yes, sir.
போட்டுமா
Slideshow, sir.
okay slide show
Yes,
now
yes, sir.
able
Now,
to-
yes, sir. Now, okay, sir. Fine, sir.
okay
Okay,
f
sir.
of
Yes.
z is analytic in a domain D, and A is a point in the domain. Since a domain, what is domain? Domain is a connected open set. Since A is a point, we can find a disk there within the domain, and mod z minus a s equal r is a domain, is a closed disk containing D. Then we can represent f of z in terms of power series. F of z can be written as a naught a1 z minus a etc. plus an z minus a power n etc. This expansion is valid for all points only in this unit disk, only in the disk, not in the entire domain D, only in the sub.
Sir, voice not audible, sir. Sir, can you hear me, sir? Sir, voice not audible, sir. Sir, sir, voice not audible, sir. Please unmute, sir. Your voice muted, sir.
Okay.
Hello.
Hello.
Sir, sir, now audible,
Mic
sir.
test.
Now audible, sir. Yes, sir. Now audible, sir.
Hearing?
Yes, sir. Now open your. Yes, sir. Yes, sir. Now fine, sir. Voice audible, sir. Sir, now open your PPT, sir. Your screen is shared, sir.
Hello.
Sir. Yes, sir. Voice audible, sir. Yes, sir. Voice audible, sir.
Hello, are you able to hear me now?
Yes, sir. Yes, sir. Now fine, sir. Audible.
Okay,
Sir.
okay.
Okay.
I will
Okay.
start.
PPT தெரியுதா screen தெரியுதா கேளுங்க.
Screen is
Sir.
visible? Okay.
PPT
Yes, sir.
தெரியுதா
Screen
கேளுங்க.
visible, sir.
Are you able
Now
to
okay,
see the
sir.
screen?
Yes,
Okay.
sir. Now, yes, sir. Now
Share your
change into
screen,
slide
sir.
view, sir. Sir, now change into slide view, sir.
Okay.
Slide view, sir.
Okay.
Make into slide view, sir.
Now, what is that? ಏನಪ್ಪ ಅದು?
Sir, please change into
Just
slide view, sir.
D is a domain and a circle is there. For the center of the circle, we know the values. What are the values? The set f a, f dash a,
Sir.
all the derivatives of the function at the point A. Only these things are known. Only these data are known. Using these data, using the Taylor's expression, we can find the value for all the points in this circle. Or for all the points, we can get it. But what is Cauchy's integral formula? That gives, if we know the value of the boundary, value of the function on the boundary, then we can determine the function value inside the circle. That is given by the Cauchy's integral formula. This is from the center, we are getting the value for all points. But Cauchy's integral formula gives that once we know the value on the circle, then we can get the value of the function uniquely determined inside this. But we are using Cauchy's integral formula for the Taylor's proof of the Taylor's expansion.
No.
Hello. Hello, sir. Mic work பண்ணலையா? Oh. என்ன சார்? என்ன சொல்றார்?
ஹலோ சார், என்ன ஒர்க் பண்ணல? இது எதுக்கு? ஸ்லைட் ஷோவா? பண்ணிடுறேன். ஸ்லைட்ஸ் ஒன்று நீங்கள் ஓகே. நான் இன்னும் வச்சுக்காதீங்க, ஒரே நிமிஷம் நான் செக் பண்ணிடுறேன். ஒரு செகண்ட். இப்போ பாருங்க, இப்போ வந்து ஸ்க்ரீன் தெரியுதா பாருங்க. ஃபர்ஸ்ட் நான் ஸ்டாப் ஸ்க்ரீன் போட்டுடுறேன். இப்போ திருப்பியும் ஷேர் ஸ்க்ரீன் போட்டு வரேன். இப்போ பாருங்க, ஸ்க்ரீன் வருதா பாருங்க.
என்ன விஷயம்?
ஹலோ, இப்போ ஸ்க்ரீன் வருதா பாருங்க. ஸ்க்ரீன் தெரியுதா? என் ஸ்க்ரீன் தெரியுதா? இப்போ பிபிடி தெரியுதா பாருங்க.
Yes sir, now PPT also visible sir. Sir please change into slide view. Yes sir, now slide view sir.
ஸ்லைடுக்கு போய்ட்டேன். இப்போ ஸ்லைடு ஷோ போறேன் பாருங்க. ஓகேவா?
ஓகே.
Now okay sir, fine sir.
Now okay.
அவர் பேசுறது கேக்குறதா?
Okay.
Yes sir.
Okay, right.
சவுண்டா இருக்கா? வாய்ஸ் ஆடியோபலா? நல்லா?
Yes sir, audible sir.
Okay, sir. Okay.
Thank you.
But what are the consequences of the Taylor's theorem?
Every 5 minutes audible.
Okay. That f of z be analytic function defined in the domain D if A is a point such that there is one point in the domain such that all the values f of A and all the derivatives at A are 0. F of A 0, Fn of A 0 for all n. That is for a particular point. What can you say about the function? Can you say that there are some more points satisfy this property? Can you say that there are some points at which f and also all the derivatives of fn vanish at that point? Yes, you can. By using the Taylor's expansion, we can do that. Now, what is given? A is a point such that f of A is 0 and fn of A is 0 for all n. And we can find a small neighborhood around the point A. D is a domain and A belongs to domain such that there is an open disk contained in the D. By using the Taylor's theorem, we get f of Z equal to. I know f of A, f dash of A, f double dash A, all these things we know. And once we are given Z in the domain, then I can substitute the value Z here and I can find the value of f of Z there. So this determines this. But what is given here, f of A is 0, f dash of A is 0, all the derivatives are 0. Therefore, what will happen? F of Z equal to 0. So f of Z equal to 0 inside the small circular disk. That means it is a constant function, identically 0 on the disk, not in the domain, on the disk. Since it is a constant function, all the derivatives are 0. So once a point is given such that f of A and all the derivatives are 0 at the point, then there are many points such that all values of fn and f vanish at those points. So those points will form a small circular disk. Now we can say something more on that. This happens entirely in the domain. Now we collect all the points for which f of A equal to 0 and fn of A equal to 0. We collect all these, they satisfy this point. Just now we have said that if A is not empty, this capital A contains a small circular disk, therefore A is an open set in D. What about the complement of A in D? That is a set of all functions for which these conditions are not satisfied. That is either f of A not equal to 0 or fn of A not equal to 0 for at least one n. So the B is a collection of all B such that either f of A not equal to 0 or some n fn of A not equal to 0. Therefore, it is a union of sets. Union where f of A not equal to mod f of A not equal, f of A not equal to 0. Union where fn of A not equal to 0, where n equal to something else. So B is also, each one is open set. It is a union of open set, therefore B is also open set. Now A is open, complement of A, that is B, is also open. So D is a union of two disjoint open sets A and B. But what is D? D is a domain. It is a connected set. A connected set cannot be written as a union of two disjoint union of non-empty subsets. But here I have written as a union of two open sets A and B. Therefore, one of the open sets should be empty. But already I have taken A, it contains at least one point. A is not empty, therefore B is empty. That means there is no complement of A in D. That is D equal to A. That means for all points in D, we get this. Therefore, the theorem says that if f of is an analytic domain D and A is a point such that f of A equal to 0 and fn of A equal to 0 for all n for a particular point, then these conditions are satisfied by every point in the domain D. F is identically equal to 0. If there is one single point where f vanishes and all the derivatives fn of A vanishes at that point A, then that is true for every point in D. That is a consequence of this theorem. What about this? This is about the complex analysis. Can you get some similar result in the real analysis? Is the above theorem true for real analysis? What is that? F is analytic. F is analytic, F is derivable. But the real analysis, F is differentiable, need not imply it is differentiable second time, third time, fourth time. So we have to consider a function which is differentiable any number of times. Such a function is called C infinity function. So I have considered a real valued function defined on the real line, which is a C infinity function. That is, it is differentiable any number of times. Suppose there is a point A such that f of A equal to 0, and all the derivatives of f at that particular point equal to 0. Just as we saw the complex analysis, can we conclude that f of x equal to 0 for all x? If the condition is satisfied for a particular point, can we conclude that that is satisfied for all the points in R? The answer is, unfortunately, no, on the real line. The result is true for complex, but it is not true for the real line. For example, consider the function up to 0, negative part, answer is 0. From the positive real axis, e power minus 1 by x square. This is not a 0 function. It is 0 up to the negative real axis and include 0, and then it is taking off above the real first coordinate. This function is not identically 0, but y of 0 is 0, fn of 0 is 0 for all these things. Therefore, there's a first difference between the complex analysis and the real analysis. Complex analysis, f is differentiable, it is differentiable any number of times. But a real analysis, f is differentiable one time need not imply differentiable. F is differentiable 100 times need not imply it is a differentiable 101 time. Even if you assume that it is differentiable infinite many times, then vanishing at a particular point does not guarantee vanishing for all points. That is a major difference between the complex analysis and real analysis. Okay, we'll come to the complex analysis. F of z is not identically 0. Not identically 0 means it is not everywhere 0. Somewhere it may be 0, but there are some points where which f of z is not equal to 0 in the domain. Then we claim that f of zeros are isolated. If there is a 0, if A is a point for f0, that is f of A 0, then I can find a small neighborhood of around the A such that A is the only 0 for the function. No other point in the neighborhood is a 0 for the function. In that case, we say that A is an isolated 0. The 0 A is isolated. We want to prove that result. Since f of A is not equal to 0, f dash of A, f double dash A may be equal to 0. But if all the derivatives vanish at that point by the previous term, f should be identically 0. But what is given, it is not identically 0. Therefore, there is at least one positive integer such that fn of A not equal to 0. So, among those integers, find the least one. Let m be the least positive integer such that fm of A not equal to 0. Then I get fm of z equal to fm of A. This first m terms cancels. F of A is 0, f dash of A is 0. So it starts from fm of A and z minus a power n. So for all these things, z minus a power n can be taken outside. Then the remaining can be grouped as that is also an analytic function in the domain. So I can write f of z as z minus a power n to g of z. What about this g of and g? What is g here? G is this bracket. Okay, yeah, g is this bracket. This is g. Substitute z equal to a. So first term is not 0. fm of a is not 0 is given. Therefore, first term is not 0. All other terms are 0. Therefore, g of a is not 0. G of a is fm of a factor m is not 0. Therefore, if the function is not 0 at a particular point, the neighboring points also it is not equal to 0. We can find a small neighborhood in which f of g of a is not equal to 0. So in this neighborhood, if f of z equal to 0 means either z minus a equal to 0 or g of z is 0. But this is 0 only when z equal to a. At a, this is not 0. For all other z, This is not 0. If z not equal to a, this is not 0. But this is also not equal to 0 in the neighborhood. Therefore, z equal to a is the only 0 for the function f in this small neighborhood. Not in the entire domain, but around this. So if z equal to a is a 0 for the function, it will not allow other zeros to enter a small neighbor. So it is an isolated 0. This is the most major important theorem because we are using this to prove that uniqueness theorem. Now, using this uniqueness theorem, suppose in a domain D there are two functions, f of z and g of z are two analytic functions defined in the domain D. In the domain D, we get a sequence. Zn be a sequence in D such that all the terms are not equal. They are distinct terms. Zn not equal to Zm. And the sequence converges to a point, and that point is also in D. So the sequence is a convergent sequence with the distinct terms, and the limit point is also in D. Suppose f and g coincide at these points, f of zn equal to g of zn for all these points. A sequence is given. On these elements of terms of the sequence, f and g coincide. Then claim is f and g coincide throughout. Then f and g coincide throughout this. So if they are identical on a converging sequence, then they are identical throughout. They uniquely determined. You can't find a different one. So here most important is the limit point z0 of the sequence should belong to D. If the limit points outside, the theorem is not valid. There may be many functions which are identical on the sequence, but they are not same. If the limit point is not in D, cannot be. So this cannot be dropped. We will give an example later. Okay. So this is more important. The limit point is not in the sequence, then the function is uniquely determined. This is called uniquely determined. There are many questions you are asking. This proof for this is I get f of z and g of z, two functions given. I consider the difference h of z. Since f and g are analytic in domain D, h is also analytic. At Zn, what will happen? H of Zn is f of Zn minus g of Zn. But at Zn, both the functions are given same value. Therefore, the answer is 0. Okay. Therefore, h of z not equal, h of Zn is 0. As Zn tends to Z0, what will happen? H of Z0 is a limit point of h of Zn is also 0. So Z0 is a 0 for the function h. And every Zn is also 0. But Zn converges to Z0. If you consider any neighborhood of Z0, since the sequence Zn converges to Z0, that neighborhood will contain, after certain stage, all the terms of Zn after n greater than equal to n. Therefore, this Z0 is not an isolated 0. Any neighborhood, every neighborhood of Z0 is a 0. It will also allow some other points also 0. Therefore, it cannot be an isolated 0. If it is not isolated 0, the function should be identically 0. Just now we have finished that. Therefore, h is identically 0. What is h? H is equal to f minus g. H equal to 0 means there is 2 equal to 0. That is f of z equal to g of z for all z. So that is a proof of the theorem, uniqueness theorem. Based on that, we do some problems. Objective type problem. They are asking one question every time. Every year they are asking one question from this type. Some may be tough, some may be easier. Let D is a set of the unit disk. I consider the D as a unit disk, and D is a analytic function. Okay, it is analytic function given that at 1 by n, sequence 1 by n, at 1 by n I know the value. What is the value? F of 1 by n is 0. Then what are all the possibilities? F is identically 0. F equal to 0 only when z equal to 1 by n, where n equal to 1, 2, 3. Or f of z equal to half for at least one point. F is a non-constant polynomial. But what is the sequence given? The sequence given is 1 by n. The 1 by n tends to 0. But domain is a unit circle, unit disk. So 0 belongs to the unit disk, center of the disk. So 1 by n converts to 0 in the domain D. So by uniqueness theorem, the function equal to 0. The f of n by n is 0 means the function f and the 0 function are same at 1 by n. Because of the sequence converges to a point, then f and the 0 function coincide with throughout. Therefore, I get the first choice. What is first choice? F is identically equal to 0 in domain D. It's a correct answer. The second, it is this also, it is everywhere 0 in the domain. But second one shows 0 only here. No, there are some more extra on all other points. Everywhere it is 0, therefore it cannot be equal to half at any point. Zero function is a constant function, therefore it is not a non-constant function. So non-constant function is the wrong answer. So for this question, first one is the correct answer. The second, third, fourth are wrong answers for this. This is a very simple problem because the sequence 1 by n tends to 0 and the limit point is also in Z, the domain D. Slightly difficult problem. FB analytic function on the unit disk, same unit disk. Which are the following? 1 or 2, maybe 2. F for every positive integer n, f of 1 by n equal to 1 by n square. Can we expect f of z equal to z square? 1 by n converges to what point? 1 by n converges to 0 as n tends to infinity. 0 is the center of the disk, it is in the center. So f of 1 by n, okay. I know the value of f of 1 by n. F of 1 by n, 1 by n square. Another function is z square. The f of 1 by n equal to 1 by n square. Therefore, at 1 by n, f and the function z square are same. So the function f and z square are same on the convergence sequence. Therefore, they are identical throughout. Therefore, this is the only function f. There is no other function satisfying f of 1 by n equal to 1 by n square. Okay. So then f is equal to z square for that. Coming to the second one. So first option is correct. What about the second option? If every positive integer n, f of 1 minus 1 by n equal to 1 minus square, can we say that f of z equal to z square? F of 1 by n is 1 minus 1 by square. Therefore, f equal to z square at these points. At whenever z equal to 1 minus 1 by n, f of z and z square are same. Okay. So f of z equal to z square is one valid function which satisfies this. But that is not the only function. Uniqueness is not there because the sequence 1 by n converges to which point? As n tends to infinity, 1 by n, 1 minus 1 by n converges to 1. But 1 is not in the disk. Disk is an open disk, unit disk. Therefore, the limit point is on the boundary, not in the disk. Therefore, this function is a function, but this is not a unique function. There are some more functions. Let us find those functions now. At least one function. It is enough. That is, the first one says that f of z is square is the only function satisfying this property. But here f of z is square is a function. That's all. But that is not the only function. There may be some other extra function satisfying this. Can we find something else? Okay. The sequence 1 by n converges to 1. This limit point 1 is not in the domain. Clearly, z square in domain satisfies this function, but this is not the only function which satisfies the given condition. Can we construct a function g such that g of 1 minus 1 by n equal to 0 for all n, but g is not 0. G is not identically 0, but g assumes 0 value at this point 1 minus 1 by n. Can we construct? Yes, it is possible to construct. How to construct that? We want g of 1 minus 1 by n equal to 0. Now let us consider. I know sin n pi is 0. Sin 1 pi is 0, sin 2 pi 0, sin 3 pi 0, sin 4 pi 0 for all n. This is 0 for all n. So this is also 0 for all n. So I compare this with this. I assume that g of 1 minus 1 by n equal to sin n pi. This is true. At 1 minus 1 by n, the value is 0 given the theorem. But here n equal to 0, it is also 0. Therefore, these two are same. G function and sin n function are identical on 1 minus 1 by n. So I want to get a connection. What is g of z? When z equal to 1 minus 1 by n, z is expressed as in terms of n. I want to express n in terms of z. What is n? 1 by n equal to 1 minus z. Therefore, n equal to 1 by 1 minus z. Okay. Substitute n value here. I substitute the n value here as a z here. So I want to substitute n value here. N value equal to 1 by z. Substitute this. So n pi equal to sin pi 1 by z. So when z equal to 1 minus 1 by n, g of z and this function coincide. Okay. So we can define g z equal to sin pi 1 minus z. This is a function. Okay. This is also analytic function. Sin pi 1 minus z is analytic function, except where the denominator is not equal to 0. Except where you said not equal to, there is analytic for all points except not equal to 1. No, except 1. So, okay. Now, already we have got a function, z square. Previously, I got the z square is a function. Z square is satisfied this function. This is not the only function. Okay. add z square with the GMZ. At 1 by 1 minus n, what will happen? At 1 minus 1 by n, this is equal to 1 minus 1 by square. This is equal to 0. Therefore, answer is same. The h of z also have the same value of the z square value. And I can write n, gs or gz square, gz cube. So various m I can put. So I get lot of functions. H of z satisfying h of 1 minus 1 by n equal to 1 minus 1 by n square. I get it. So instead of this, this is what will happen. With z square is one function. I add the 0 here. At the another function which gives 0 value at these points. So instead of this, I give a value function here which gives one value here. So z square plus 0. Instead of that, I square z square into 1. So sin n pi by z, what will happen? N z equal to 1 by n. Then what will happen? This is sin n pi. Sin n pi is 0. E power sin n pi is e power 0 is 1. So z square into 1 is z. So these functions also give the same value. So z square is not the only function. I can get plenty of function by adding g of z power m for any m, or by multiplying this, or combining these two, etc. So there are infinitely many functions giving that. Go back to the previous one. This is not the only function. I have produced infinitely many functions. By just getting a function which is 0 on this given point, but d is not 0, comparing sine function, cos function, e power function, etc., I can get this. Okay, this is a technique. The technique is just g of 1 minus 1 by n. This 0 means make it sin n square. So I want to get a connection between this and this. If this is z, what is n? Substitute the value n. I get the value function. So I guess this is a function. This works, and add with that z square plus 0 at these points. So I get it. So this is a major technique for all these problems. Okay. Oh, some more. Okay. There are two more questions in the previous. Okay. Carry the f of 1 by n equal to minus 1 by n. That means what will happen? 1 by 2, answer is 1 by 2. 1 by 4, answer is 1 by 4. 1 by 6, answer is 1 by 6. So identical function. So 1 by 2, answer is 1 by 2. Answer 1 by 4, answer 1 by 4. Answer 1 by 6, answer 1 by 6. It is just like identical function. Okay. But if it is a 1 by 3, minus 1 by 3, 1 by 5, minus 1 by 5, is a negative function. So I get value here, z function, also minus z function. F cannot satisfy these two. So this f cannot satisfy this. This is a true statement, therefore this is okay. What about the next one? Can it satisfy f of 1 by n equal to 1 by s? Yes, we can find. Put this is equal to z. Z equal to 1 by n. I want to write n in terms of z. What if z equal to 1 by n? What is n? N is 1 by z. Substitute n equal to 1 by z here. So 1 by z plus 1 is 1 plus z. Z by z plus 1 is a function. So there are a function. Therefore, given it is cannot. No, I have produced a function f of z equal to z by z plus 1 is a function. Therefore, this fourth one is wrong answer. Okay. Now next problem. F is a meromorphic function which is analytic addition equal to 0. F of 1 by n equal to n by 2n plus 1. What is f of 0? F has a simple polar is equal to 2. F of 2 equal to 1 by 4. No such a meromorphic function exists. These are the choices. Which one I have tried? Can I get a function now from this? F of 1 by n equal to this. Can I get a function? I put z equal to 1 by n. If z equal to 1 by n equal to 1 by z, substitute n equal to 1 by z. So I get 1 by z, 2 by z plus 1. That is 1 by 2 plus z. I get the function 1 by 2 plus z. Okay. I get a function 1 by 2 plus z. So f and g agree on this g of 1 by n. Okay. And the 1 by n tends to 0. 0 is a point in the circle, within the circle, within the disk. Therefore, by uniqueness theorem, g equal to this. So f and g coincide with this, and therefore the function is this. Now I can answer other questions. What are the questions? What is f of 0? I know f of z. Substitute z equal to 0, I get 1 by 2. This is correct. What about the pole of the function? Pole of the function is make the denominator equal to 0. 2 plus z equal to 0. Z equal to minus 2 is a pole. But what is given there? Z equal to is a pole is given there. It is not. The answer z equal to is a pole is a wrong answer. Okay. And what about f of 2? F of 2 z equal to 2, substitute z equal to 2. I get 1 by 2 plus 2 is 1 by 4. That is also right. Okay. So, okay. F of 0 equal to half is correct. F of 1 has a simple pole at 2 is wrong. F of 2 equal to 1 by 2, 1 by 4 is correct. No such a function. But I have exhibited a function. 1 by 2 plus z. Therefore, this fourth one is also wrong because I have given a function. The fourth one is also wrong. Okay. Similar question. F of 1 by n equal to 2n by 3n plus 1. Okay. 1 by n tends to 0. 0 is in the domain. Therefore, we can find what is that? 1 by n. Substitute 1 by n equal to z. Z equal to 1 by n. Substitute here. I get 2 by 3 plus z. Okay. Then find out what about the 0 here, etc. We get the value for this. This is try with this function z by 3 plus z. How we got that function? Just I put z equal to 1 by n. Then n equal to 1 by z. Substitute the value here. 2 into 1 by z, 3 into 1 by z plus 1. Then that is simplifying this function is this. Now you can answer the question. Okay. Next question. D is an open disk. Is it possible to find a function f satisfy the condition f of 1 by n equal to f of minus 1 by n equal to n by n plus 1? Okay. Okay. What will happen? F of 1 by n. If you substitute z equal to this, I get the value is 1 by 1 plus z. If I substitute this minus 1 by z plus z, by using this I get one sequence. I get another function. But a uniqueness function, the fourth function should be same. But I get the different function. Therefore, it is not possible. So, therefore, it is not possible. Is it possible? No. Answer is no. Now, this is another good example. All these questions are dead questions. Now, consider the disk mod is less than or equal to 3. And f is an analytic function given. I don't know the value. Function is given. A sequence is given. What is a sequence? 1 plus I root 2 by n. Sequence is given. Here, I know the value of the function minus 2 by n square. Now, question is, at root 2, what is the value? The 4 values are given. Which one is correct? Okay. So, what about the sequence? 1 plus I root 2 by n. As n tends to infinity, what is the limit point of the sequence? This tends to 0. Therefore, this limit equal to 1. 1 belongs to domain. Therefore, this sequence converges to 1. If at all there is a function, there should be a unique function satisfying this condition. Okay. How to find the function? I want to write this as z. I want to write this as z. Z equal to 1 plus I root 2 by n. Find the value of n in terms of z, substitute here. That is a technique. Okay. That is given here. There's 1 by n tends to 1. That it is given that 1 plus root 2 by n equal to substitute z. Then n equal to I root 2 by z minus 1. Then z equal to this, f of z equal to 2 by n square. Substitute for n square, z minus 1 square. So the f of z, one function, z minus 1 square is another function. These two functions are identical on the sequence. The sequence converges to a point in the domain. By uniqueness theorem, these should be equal for all. Okay. So I have found out the function. But the question is not that. What is the value of f of root 2? So I know the function. Okay. Substitute root 2 for z. Substitute root 2 in z. I get root 2 minus 1 whole square. That is 2 minus 2 root 2 plus 1 equal to 3 minus 2 root 2. That is a correct answer. The correct answer is 3 minus 2 root 2. They have given combination 3 minus 2, 2, 3 plus root 2, 2 minus 3, 2, etc. This first one is a correct answer. This is a correct answer. All the other things are wrong. So I think you may guess that how I have found out the function. I take this value as z. Z is represented in terms of n. Now represent n in terms of z. Substitute that value of z, n value here. I get the function. That is a clear technique. Simple technique. Okay. If you understand this one. As there exists analytic function f of 1 by n equal to minus 1 power n. Okay. But domains are different domain. First domain is a unit disk. In the first domain, what will happen? Yeah, 1 by 2 answer is 1. 1 by 4 answer is 1. 1 by 6 answer is 1. 1 by 8 answer is 1. If the sequence 1 by 2, 1 by 4, 1 by 6 converges, f converges to 1. So f of 0 should be equal to 1. If 1 by 3, 1 by 5, 1 by 7, I take it should be equal to -1. Okay. So if I take 1 by 2n, that converts 0, therefore f of 1 by n converts f of 0 should be 1. But at the same way, if I take 1 by this, f of 0 should be equal to -1. F of 0 should be one direction. Equal to -1, the both possibilities are not possible. Therefore, there is no such function. If domain D is the unit disk. Now, if the domain D is this, answer is different. There are functions. There is not only one function, there are functions. How to find that? Okay. Now, if D is a disk, this, okay. What is a disk? This is a circular disk with center 1, radius 1. The 1 by n tends to 0. That 0 is not on the circle. It is on the boundary of the circle. Note that f of 1 by n, 1 by 4 tends to 1. F of 1 by 3, 1 by 4 equal to -1. So I want a function which takes at even values 2, 4, 6, answer is 1. And at 3, 5, 7, answer is -1. I know cos n pi. What is cos n pi? Cos pi is -1. Cos 2 pi is 1. Cos 3 pi is -1. So cos n pi is -1 if n is odd and equal to +1 equal to even. So I compare this f with that. Okay. I compare these things are even this. So I find out that f of 1 by n equal to, okay, equal to cos n pi. So I take f of 1 by n equal to cos 1 pi. Okay. F of 1 by n equal to cos n pi. But 1 by n equal to z. Z equal to n equal to 1 by z. Substitute z equal to n by n equal to 1 by z. Therefore, this is the one. So I can take f of z equal to cos pi z. Okay. Instead of this, I can also take the function e power I pi z. When z equal to 1 by n, what will happen? Z equal to 1 by n, e power pi by 1 by n, e power I n pi. E power I pi is -1, e power I2 pi is +1, e power -3 pi is -1. This also satisfies this. So I can take this function or the combination of this. There are plenty of functions are there. So I have considered a lot of functions. Note that the sequence converges to a point not on this, it is on the boundary. Not on the circular disk, it is on the boundary. Okay. In that case, I can find a lot of functions. The new function cannot be analytic at the point 0. The sequence converts to 0. The 0 becomes a boundary. I have defined a new function, cos. The function cannot be analytic at 0. If it is analytic at 0, 1 by n tends to a point where it is analytic. By uniqueness theorem, answer should be 0. Okay. Therefore, the point cannot be an analytic point. Therefore, this should be isolated singularity. What type of singularity? Can it be a pole or essential singularity? For these functions, cos, etc. I can write. Z equal to 0, it is not. Cos pi by z is analytic everywhere except z equal to 0. E power I pi z is analytic except z equal to 0. So z equal to 0 is an exceptional point, isolated point. What is the isolated point? Is it a pole or essential singularity? For that, I want to know the properties of analytic function. F is analytic function defined like disk. At the A, I don't know. This is the angular portion I have defined. The function is defined at z equal to A. It is not defined function. Is a removable singularity. And what will happen as Z approaches to center A? Z approach to A. F of Z tends to a finite limit, then it is a removable singularity. As Z approaches to A center, the function tends to infinity, that is a pole. If tends to any value, if given a value, I can find a sequence tends to a limit. I can find another value, another sequence. Here, a lot of sequence can be done. That is the small neighborhood of the point. Okay, if it is a removable singularity, the f of z tends to a finite limit when z tends to A. It is a pole, it should be infinity when z tends to A. What will happen here? I take a small neighborhood around A, deleted neighborhood. The image of small neighborhood is the entire plane. It is dense in the plane. All points are closed sets in this. So given any point, given any circle here, that circle could contain in many points here. So given any point, okay there. Okay. Now coming to this. Answer this. What is happened? This cos pi z at 1 by n. 1 by n tends to 0. What will happen? The f of 1 by n tends to 1. So the one way a limit equal to 1. Another way a limit equal to -1. Another way limit may be equal to -I. Another way limit equal to. So whatever be the value given, I can find a sequence converging to 0 such that the value is taken. that means it is not a pole because it is not tending to infinity, it tends to 1. It is not a finite value. It is not infinity. And also equal to -1. The value is not unique. Therefore, the function has essential singularity at that point. So for all those functions defined by this, what has happened? The secant converges to a limit point, then we can find a function satisfying this property. Those functions have that particular limit point as essential singularity, not pole. Okay, this will help you to find out set of functions. Okay, now this is a simple problem. F is an entire function. Entire function means it's analytic everywhere, analytic in the entire complex plane. F, what is given? Whenever Z is real, f of Z is real. Okay, then f and the other functions are same. F conjugate of Z, conjugate of f of Z. Z bar, f of Z bar, but this function is analytic. This is also analytic. When Z is real, what will happen? When Z is real, Z bar is real. When Z is real, Z bar is real. Therefore, I get f of Z. F of Z is real. Therefore, f of Z bar equal to f of Z equal to 6. Therefore, these two functions are identical on every point in the real line. Real line, we can find a sequence converge to 0. So, these two functions are same on the sequence which converge to a point in the domain. Therefore, by uniqueness theorem, these two are equal. Okay. Similarly, when f is real, then it is real. When Z is a purely imaginary, f is imaginary, I can prove that f of minus z is equal to f of minus z. This is a simple problem. This is an important theorem also. This has another consequence. F is an entire function. If a is greater than 0 is a number, f of z is a real number. A is given. Some real number is given. What is given? F is real on the real line. F is also real, then the imaginary part of z equal to z. So what about this z? Z equal to x plus ia. X is a real number. X plus ia is imaginary part is a. So for those things I get. Okay. Then is it possible? F of z plus ia equal to f of z minus ia. F of 2 plus ia equal to, this is true for all z. Is it true for all z? These are the questions. Okay. Then let us answer. F is a real. This first one I answered. What is that? When z is real, then z is real. F of z bar equal to f of z equal to this. So the function f of g assumes same values of the real line. Therefore, they are equal. Now, additional property is whenever imaginary part of z is equal to a, that is also given. So I consider f of z minus ia. When z is real, z minus ia conjugate is z plus ia. So what is it? F of z equal to f of z bar bar. So when z plus minus ia, when z is real, I get this is equal to z plus ia bar. So z plus ia bar. For this function z plus ia, z is real, it is given. Therefore, what is imaginary part? Imaginary part is a. When imaginary part of a, f of z is real, it is given. Therefore, this value is real. Therefore, the conjugate value is same. Therefore, this value and this value are same. Therefore, this value is true. So, first option, this option is true. When this option is true, whenever z is real. Whenever z is real means these two functions are identical on the real line. Therefore, by uniqueness theorem, they are identical on the entire plane. Okay. Now coming to the second one. Second one, is it true for the second one? Second one is f of z plus I to a. I write this f of z plus I to a is f of z plus ia plus ia. But just now I have seen that f of z minus ia equal to f of z plus ia. So this is something plus ia. So I can write this f of z minus a minus ia. Minus ia plus ia get cancelled f of z. Therefore, f of z plus ia, I can write this f of z plus ia plus ia. This is some complex number plus ia. For that, I can write minus ia by the second property. Therefore, I get. So this is true for that. The second condition is also true. The B option is also true. What about this? Is f of I plus a equal to f of z true for all? That is not true. It is true for 2a, but not a. Okay. This f of z plus a is true for all such functions. The question is, what is the question? Not only for one function. Whenever f satisfies this property, for all such entire functions, this may be true for some function, but may not be true for another entire function. So is it true for entire function? That is a question. So if it is not true, I want to give an example of an entire function for which this is not true. Okay. Now consider f of z equal to e power z. My a equal to pi, a equal to pi. A equal to pi. So f of z plus I equal to f of z plus I pi equal to f of z into e power I pi. E power I pi is -1. Therefore, minus e power z. What is my function? E power z. When I substitute z plus I get e power minus z. These two functions are not same. E power z and e power minus z are not same. This is a real number when z is real. But when a equal to this is a real number, but the negative of the real number, therefore they are not equal. So the fourth one, the third condition, this is not valid for one function, but f is e power iz and a equal to pi. Okay. Okay. These are questions. Students can take this question. I can answer it leisurely at home. You can think is, does there exist a function which is analytic in open dissatisfied? These functions are given in the next questions. So this is a collection of questions. So f of 1 by, what is the disk? It is defined with disk 1. F of 1 by n is 0 for odd positive integer, equal to 1 for even positive integer. Is it true? And 0 for n odd, 1 by n for n is even. Similarly, these things are, you can take it, these questions, take down these questions, you can answer leisurely, think it over that. Just uniqueness theorem, okay? Whether the limit point exists, if they are not equal, we get it. Similarly, these are zeros for the function, I omit these things, okay? Next. F is anti-function D and G is anti-function. This is also I can omit now. Then coming to Cauchy's estimate. F of z is analytic in the domain D and A be a point in the domain. I can draw a small circle disk within the domain D with center A and radius R within the domain. On the bound on the circle, it is given that it is bounded. F of the circle is a compact set, therefore it should be bounded. It is bound is also given M. F of z less than equal to for all z on the circle, not within that. Cauchy's estimate said, what is F1 of A? F1 of A less than equal to this. This is the upper bound for this F1, modulus of F1 of A. This is the estimate given by that. When n equal to 1, substitute n equal to 1, I get this. This is Cauchy's estimate for f dash. Okay. Proof is very simple. What is F1 of, there is a formula for F1 of A, n factorial by 2 pi I this. I take the modulus on both sides. I take the modulus is less than equal to n factorial. Modulus 2 pi is pi. What is modulus f of z? Modulus f of z is m. What is modulus z minus psi minus a? Psi is on the circle. A is on the center. So distance between a point on the circle and the center is radius r. Therefore, this is equal to r. R power n plus 1. Okay. So I can take capital M by r power n plus 1. I can take it. And therefore, integration of the d psi. D psi is the length of the circle. Length of the circle is a perimeter is 2 pi r. So value is n factorial by 2 pi into m into 2 pi r into r power n plus 1. 1 r get cancelled. Okay. And 2 pi get cancelled. So I get factorial n by m by r. This is the estimate given there. Okay. When n equal to 1, I get the value. So these two are more important. I want to use it frequently. Then the Liouville's theorem. A function is an entire function. Entire function means it is analytic everywhere in the domain, everywhere in the complex plane. It is also bounded. That means image f of z, f of that is set in the complex plane. I can enclose it in a big circle, big disk. So it is a bounded. The theorem says that bounded entire function is always a constant. This is a well-known theorem. Okay. Proof is very simple using that. What is given? F of z is less than equal to m for all z in C given. Okay. And A is a point. Note that. What is that? It is bounded given. Therefore, bounded means that there is some m such that mod f of z less than equal to m for all z. A be any point. Consider the circle mod z minus equal to r. R may be any radius because my plane is by domain is the entire plane. Therefore, I can take a radius, any radius. R may be 1000, 2000, anything, or 1 by 100, anything else. So I can take a circle here. By Cauchy's theorem, f dash of a is less than equal to Cauchy estimate mod f dash of a is less than equal to m by r. But this r, m is fixed. But r is, I can take r equal to 1, r equal to 2, r equal to 5. I can increase r at my will. It is true for every r. As r tends to infinity, what will happen? This denominator tends to infinity. Therefore, this tends to 0. Therefore, f dash of a is 0 for that. This is true For any point, I have taken any point. So f dash of a equal to 0 for all means f dash is 0 throughout. Derivative of the function is 0 means the function is constant. Derivative is 0 at all points. Therefore, the function is a constant function. That is a simple proof for the Leibniz theorem. But this theorem is more important. Even though proof is simple, this gives a lot of information. Okay. Similarly, this is a first. Okay. Let f of z be an entire function with m. The previous theorem says that mod f of z less than equal to m. That's all. Mod f of z less than equal to m into mod z power m. Okay. This is true for a bigger circle. Then the function should be a constant. If m equal to 0, what will happen? M equal to 0 is a constant function. Okay. If m equal to say 10, then it is a function of 10. Okay. We get this. Okay, we are using this. We assume the result of this. We can prove it. I know what is the value of fm of ZA. Take any point, fm of ZA. Just like the previous, this one, same way you have to find out. We get R there. Okay. Hello. Now next function, f of z be an entire function such that f is real in so that f is a constant function. Hello. Hello. Let f of z be an entire function such that f of z is real. Not real for f of z entire function. F of z is not real. Show that f is a constant function. F is not real means the f of z is not on the x-axis, real axis. Image will be everywhere, but except the real point. Then the function should be constant. We can't use the Leibniz theorem just. Leibniz theorem says if it is bounded, it is not given as a bounded, it is not real value. F of z will not assume real value. F of z, imaginary part of f of z is not 0 for any z. Show that f is a constant function. F z is not real for all z. To each z, what will happen? Imaginary part is not 0. Either it may be 0 greater than 0 or less than 0 for each. But because of the connectedness, we can collect all the points for which imaginary part is greater than 0, one set. For all points for which imaginary part is less than 0, both the sets are open sets. Disjoint open sets for the connected. But C is connected. Therefore, one of them is empty. Either this is equal to empty set or this is equal to empty set. Therefore, we get either imaginary part is greater than 0 for all points. Here it says that for each point, this is possible or this is possible. Because of the connectedness, I get either this is 0 for all z or this is 0 for all z. I assume this. We can prove that it's a constant. Same proof. Now we can assume that f of z is the upper half plane. F of z is the upper half plane. -1 is not in the image. F of z is the upper half plane. -1 is not image. So whenever f of z is a point, I can find the distance between -I and this. This distance is already getting equal to 1. This is shortest distance is 1. Therefore, distance between f of z and -1 is greater than equal to 1 for all z. So what about 1 by f of z? Modulus is less than equal to 1. Therefore, it is an entire function. This function is not defined only when f of z is equal to -I. But f of z is in the above. It is not equal to -I. Therefore, this is never 0. Therefore, 1 by f of z by is an entire function and it is bounded by 1. So, it is a constant. Therefore, 1 by f of z plus I is constant. Means the reciprocal is also constant. I is a constant. Therefore, f of z is also constant. So, I get a constant function. I use the Leibniz theorem, but not straight away. I use that. It is away this. So simply verify this proof. The f of z is here. And I have taken a point outside the range. And there is a positive distance between them. I, -I and any point. This is getting equal to 1. If this is to happen, the function should be constant. That means this point is not in the range. And there is a small neighborhood also not in the range. That means -I is not a limit point of this. -I is not a contact point of the image. That means the image is not dense. Then we get a constant function. Just a replica. F of z is a non-constant entire function. The image should be dense in C. Non-constant given. So image should be dense. So given any point, given any circle, I want to show that there is at least one point here. Assume that there is a point At least there is a small circle bit such that f of z, all the f of z are away. Then distance between a and f of z is always getting equal to some delta, some epsilon. So 1 by f of mod f of z minus a is less than equal to something. Greater equal to, therefore less than equal to. So 1 by f of z minus a is a bounded function, entire function, constant, therefore f of z constant. This is bounded, therefore f of z minus a is bounded, therefore f of z is bounded. So I get this. So this is one. But what is Liouville's theorem? Liouville's theorem says that if f is bounded, then it is constant. The next property says that if it is not dense, then also. But another beautiful theorem is there that is called Little Picard theorem. Proof is difficult, slightly difficult. Most of the MSc students will not know this because this is not included in the syllabus because of the proof technicality. But you can assume this result. What is the result? If f of z is an entire function, either it should be a constant function. If it is not constant, what about the image? What are all the points not in the image? Suppose you can find 2 points alpha and beta. If there are two distinct complex numbers alpha and beta which are not in the image, so image omits 2 points, then f must be a constant. It omits everything except 1 point. It's a beautiful result. Yeah, if f is a non-constant function, it takes either the entire complex plane or it can omit at the most 1 point. If the range omits 2 distinct points, the function should be a constant. Kind of take the polynomial. Polynomial is the entire function which take all the values. Given any value, I can find z such that polynomial f of z equal to this. What about e power z? Is it an onto function? E power z is analytic. Can the image of e power z is entire complex plane? What about 0? Is e power equal to 0 for any z? No, e power z is not equal to 0 for all z. So the entire function e power z takes all the values in the complex plane except one exception. What is exception? Z equal to 0. It omits only 1 point. That is allowed. If it omits 2 points, alpha and beta, you should be a constant. So we are going to use this result for a small theorem. For example, if it is given that the range is in between, the imaginary part of the f of z is bounded, then what will happen? Range is in between a circular disk. In between a disk, 2 points are omitted. Therefore, it should be a constant. Okay. This note this theorem. Proof it. Forget that proof. This theorem is useful to answer certain questions, yes or no. Okay. Now this is a question f is an entire function. Mod f of z less than equal to z power n. Okay. Then is it a function identically 0 or a polynomial or a constant equal to z? Okay. Right? It may be a constant, but I am saying that f, what are all other? Just now we have mentioned that this is theorem. Note that if an entire function satisfies this property, mod f of z less than equal to then it is a polynomial of degree less than or equal to m, not greater than m means it is a polynomial. So any polynomial of degree less than equal to m satisfies this property for suitable m. In this problem, it is given as m as a 1. That's all. Okay, therefore f is a polynomial of degree less than or equal to n. So it is a polynomial. It is not always 0, not always identically 0. There are, take any polynomial with the degree less than or equal to n minus 1, you will get it. Okay, constant is one example, but constant is not. We can take any non-zero constant. This is also there. Okay. முக்கியமான ரிசல்ட் சொல்லிட்ட பரவாயில்ல, சரி நான் கண்டிப்பா. ஓகே ஓகே ஓகே.
ஹலோ
அவர்தான்
sir. Sir, yes sir, voice audible sir. Sir.
ஹலோ
Sir, yes sir, audible sir, voice audible sir.
பிபிடி ஆன் பண்ணுங்க. இது தெரியுது, பிபிடி ஆன் பண்ணுங்க. ஹலோ, now visible? Oh.
Yes sir. Now open the PPT sir.
Oh, okay.
Yes sir. Yes, sir. Okay sir, now make it to slide view sir. Slide view sir.
Slide view.
Slide view.
Slide. Okay now?
Yes sir. Yes sir, now fine sir. Okay. Hello? Sir. Yes sir, fine sir. Now hello? Okay sir.
Okay.
Okay sir. Okay sir. Okay.
5 minutes later.
Hello, okay.
Now, fine. Yes sir, fine
hello?
Sir. Now okay.
Yeah.
Yes sir, now audible
hello?
Sir. Yes sir, audible sir. And screen.
Hello.
Hello sir.
Can you
sir,
hear
okay,
me?
Sir. Yes sir, voice is audible sir.
Hello.
Sir, voice audible sir. Okay sir.
Okay.
Could you
Okay.
hear the voice?
Okay sir. Okay sir. Yes sir. Fine
Could you
sir.
see
Everything.
the full screen?
Yes sir, full screen sir.
Thank you,
Everything
sir.
okay.
Every 5 minutes tell to any one of you and can hear like that.
Okay.
Okay.
Now,
sir. Now
we
fine.
consider
Thank you sir. Thank you sir.
we
Okay.
consider the problem.
proceed கரெக்ட்டா கிளியரா
Okay.
இருக்கு 2 நிமிஷம் தான் போகுது.
Okay. F is an entire function such that mod f dash of is less than
நீங்க
equal to
கேளுங்க
z.
every 5 minutes
Okay.
கேளுங்க.
And the next question is mod f dash of z less than equal to mod f of z. We have to find out the characteristic functions. What are the functions? In this case, it is equal to a plus b square. A, there is no condition on A, but there is a condition on B. B should be a compressed and satisfy this property mod B less than equal to half. We want to prove that. Okay. For that, I want to use the de Broglie's theorem. What is the de Broglie's theorem? Bounded entire function is constant. Somehow I want to get a bounded function. Here it is given that mod f dash of z less than equal to this. If I bring this the denominator, mod f dash of z by mod z. Okay, if I bring it to the denominator, then this is less than equal to unbounded. But that function is entire function. If that is an entire function, it's okay. Otherwise, I have to make a small adjustment. Okay. So what I have to do? I take this here, f dash of z by z. I consider the function g z here. So I consider function g z by z. It is true. It is not defined. Yes. It is not defined where at z equal to 0. So I define for all z equal to 0. Okay, mod f dash of z less than equal to z. When z equal to 0, then this is equal to 0. Therefore, f dash of z equal to 0. Therefore, z into g of z, and z into g of z means z can cancel f dash of z. That equal to 0. Therefore, at that point also I can give the value. Even though this is not defined at z not equal to 0, at z 0 I can give the value equal to something I can give. Therefore, g z is an entire function with the substituted value at z equal to 0. Okay, but what about this? Mod g of z is less than equal to 1. So this is less than equal to 1 for all places except z equal to 0. But z is a limit point. Therefore, the limit point also the value should be less than equal to 1. So entire value is equal to 1. The limit also was equal to 1. Okay. Therefore, this g is a bounded entire function. Therefore, there is a constant. What is that? This function is a constant equal to k. Therefore, f dash of z is equal to k. So f dash of z equal to k z for all z except not equal to 0. Okay. At z equal to 0 also true. At z equal to 0, f dash of 0 is 0. I have proved. Therefore, this function f dash of z equal to k z is true for all z. Okay. This is f dash where k is a constant. What about the constant? Modulus this. Modulus is less than equal to 1. Therefore, mod k less than equal to 1. Okay. This is f dash. What is f? So differentiate this, integrate this. Yeah, that is equal to a plus b z square. Actually, we get it. What is b? Actually, I get k into z square by 2. Integration is k into z square by 2 plus a constant a plus k by 2 z square. K by 2 I have taken b. So mod k is less than equal to 1. Therefore, mod b is less than equal to half. So I have defined the function as. Okay. So the first one I answered this. Okay, just to bring it here, that is the entire function. Except it's not defined at z equal to 0. At z equal also remove singularity, I can make it an entire function. Therefore, I can bound an entire function. Liouville's theorem. Liouville's theorem is more important. Next, I want to get it. Okay. So same thing. Mod f dash f less than f of z. Can f of z equal to 0? There is something greater than. This value is 0. It's not negative. Therefore, this modulus is always greater than 0 because of this. Therefore, f of z is not 0 anywhere. So f will not vanish at any point. Therefore, I can divide by this. F dash of z less than this. I can bring it to the denominator. So I can find f dash of z by f of z. Modulus value is less than 1. So I get the function f dash of z by f of z, entire function. That is also bounded. So a bounded entire function is a constant. Therefore, mod f dash this is equal to a. Therefore, I can f dash of z equal to a into f of z. What about second derivative? A into f dash. For f dash, substitute the value. A into f dash, but f dash I can substitute the a into f of z. Therefore, a square into f of z. Once again differentiate. I get a square into f dash. So I get a cube into f of z. So I get fn of z equal to a n for all n. So my f of z equal to f of 0. Terrace expansion. Okay. F of 0 plus a into plus f dash 0 into f dash of 0. What is f dash of 0? F dash of 0 is a into f of 0. F double of 0 is a into a square f of 0. So I get a into f of 0, a square, etc. For all these things, f of 0 is common. I can take it outside. So 1 plus a is by factorial 1, a square is by factorial 2. So this is just like 1 plus x by factorial 1, x square by factorial, etc. e power exponential. So this is f of 0 into e power a z, where this is the z. This by factorial 1, this square by factorial 2, therefore this is. So what is f of 0? I don't know the value. I can't take it k. Value f of 0. So my value is k into e power a z. Only condition, there is no condition on k. K may be 0. K may be, but there is a condition for a. What is the condition? A is less than 1. So my function is f of z is set of all k such that set of all functions such that k into e power a z with one condition mod a is less than 1 because of this. Okay. Just to improve this previous theorem. Okay. F is an entire function and the mod f dash is less than equal to f of z here. What is the previous question? Previous question is mod f dash is less than f of z. Because of this, this is not nowhere 0. I can break it. But if this is less than equal to 0, what will happen? The question is less than equal to 0, what will happen? Okay. The question is mod f dash is less than equal to f of z for all z. This is a set of all functions satisfying this property. Set of all entire function for which this condition is satisfied. Is it a finite set, infinite set, or this, or same thing, but there is a condition for a here. There is no condition on a, but there is a restriction on a. So these are 4 choices given in the next question. First, if f is a constant function, what about derivative? 0. For a constant function, this function is satisfied, this inequality is always satisfied. So every constant function satisfies the condition. So the f contains all the constant functions. How many constant functions are there? Lot of constant functions. Therefore, the set is not finite set. There are infinitely many constant functions are there. Therefore, f contains constant functions. Therefore, f is not a finite set. First one is wrong. The second one is correct. I want to select this, or both may be wrong, or one of them is right. Which one? I want to work it out. Okay. Inequality f is satisfied whenever f is constant. Note that these functions given here, for these functions also, this is my f of z. What is the differentiation of f of z? B into e power a z into a. Therefore, f dash of z equal to a into f of z. So modulus equal to a into mod f of z, mod a less than equal to 1. Therefore, the condition is satisfied. Okay. So these functions are also in this set. So first question is answer is wrong. That is a finite set is wrong. Second one is wrong. What about the third one? For example, I take f of z equal to 3 into e power 4 z. What is third one? Third one, I have, there is no restriction here. There is no restriction. I take a, but restriction is the single one here, but there is no restriction. So I take 3. What will happen? I take 3. F of z equal to 3. If f of z equal to 3 into e power z, what is f dash of z? 4. What about modulus? This is greater than or equal to 4z. Therefore, condition not satisfied. Therefore, third one is also wrong. What about the fourth one? Fourth one, the same thing. This answer is same thing. Fourth one is the same thing. What is that? F of z should be same thing. F of z equal to k into e per z. That is a condition only for a. Mod a is less than equal to same thing. Instead of that, they are given alpha and beta. That's all. Okay, same thing. Provided, okay, I can take this f dash of z, but I want to prove that f of z is not 0 anywhere. If this condition is satisfied, just if this condition is satisfied, f is a non-zero function, f is a non-constant entire function. If this condition is satisfied, then f never vanishes in C. We want to prove it. It's a strong result. Okay, that is f of z cannot be 0. Suppose there is a point A where f of a is 0. Okay, if f of a is 0, at a f dash is also 0. So z equal to a is a 0 point for f and also f dash. That means z equal to a is a multiple 0 because the derivative is also vanishes. It's a multiple 0. What about the order? So it is equal to order equal to m. So f of z can be in z minus a power m divided. Therefore, f of z can be taken z minus a power m into some other entire function. Similarly, what about this for f dash? If the order of the 0 for f of z is m, the same is 0 for order m minus 1. So this can be written as z minus a power m minus 1 to some other function. When we put the modulus where z not equal to 0, I can cancel the z minus a power m minus 1 to z minus a power. So I get that f dash g of z less than equal to mod z minus a into some other function. As z tends to 0, this also tends to 0, that also tends to 0. We get a contradiction. Okay. Therefore, the function never vanishes. If this condition is satisfied and f is a non-zero function, this function never vanishes. Therefore, I can bring it to the denominator. That denominator never vanishes. Therefore, it is an entire function. Same argument proves the theorem. Okay, just one simple difference, but I have to prove that this cannot be equal to 0 for any z. Okay. Now, f of z is a meromorphic function such that mod f of z equal to z whenever f is analytic. Meromorphic function means function is analytic everywhere except certain points. Those points are poles. Poles are allowed. Okay, except for poles, the function is analytic everywhere. Whenever f is analytic, this is given is mod f of z equal to mod z. But f is analytic not everywhere except certain points. This is analytic. So I can't use Riemann theorem straight away, but I am going to use the straight Riemann theorem, but not straight away because it is defined only where it is analytic. But by this I can bring it here. Mod f of z I can bring it here. Therefore, z mod z means mod z means z equal. Therefore, I get a bounded entire function. Okay, but the f of z may be equal to 0 somewhere. Okay, if mod f of if z is not equal to 0, if z not equal to 0. This value is positive, therefore this value is also positive. F of z can be 0 only at z equal to 0. Nowhere it is equal to 0 except 0. Okay, 0 is the only exception point. There I have to find out. Okay, the options are no such function exists. Such a function must be entire function. There is a unique function satisfying the given condition. There is an A satisfying these properties are given. I will answer this question one by one. If function is a meromorphic function, therefore in analytic except certain points pole, I take all the poles. A collection of all poles. A is a set of all poles. Note that poles are isolated. That means given a pole, I can find a small neighborhood such that it will not have any other pole except the given pole. So I can enclose this by means of small circle containing only one pole. Therefore, A is set of all isolated poles. The 0 may be a pole, may not be a pole, but I have included because at 0 f of z may be 0. Therefore, I include that A. Therefore, D equal to the complement of. Here, F is analytic at the domain D. It is a closed set, therefore it is open. It is a domain D. You consider the function Z by F of Z. Okay, what is given there? F of Z by the function is this. I have to bring it to the denominator. That function is G, Z by F of Z. I consider this. This function is present on D, not on the entire plane, only on this domain D. But to each point in B, I can get a small neighborhood in which Z equal to B is the only troublesome point. All other points in the BD. So in all other points, mod G is less than equal to 1. Except that point B, mod G is less than equal to 1. But G is, that means that point is a removable singularity. It is not a pool. Okay? It is a removable singularity. Therefore, G is also analytic at that point. So G is analytic every point in B. So G is analytic every point in B means G is analytic everywhere. That means it is an entire function. Okay? So first question is, the second one is right. Such a function must be an entire function. No other. It must be an entire function. No such function exists, wrong, because we have proved that that me must be, but I have to give an example. Examples are given here. Condition 4. What is it? Mod f of z equal to a z. What about modulus? Mod f of z equal to mod a into mod z. So when mod a getting 1, mod f of z getting mod z, their functions are there. Plenty of functions are given. The question itself given. Therefore, no such function exists out. Okay. There are a lot of functions here. I can change the value a equal to 2. Yes, that is a function. A equal to 3, I get a function. A equal to 4, I get a function. Therefore, the unique function, that condition is wrong. So the red line, no such function is wrong. Unique function is wrong. This is correct. But I want to know, these are the functions, okay. But we have to say these are the only functions. There is no other function which cannot be written in the form. Then only this is correct. These are examples, okay. But I want to show that this f must be equal to this one. Okay. In fact, it is true. Since G is bounded, D of Z is equal to 1. Therefore, what will happen? Therefore, this is a bounded function, this is a constant. Therefore, Z by f of Z equal to A. Therefore, Z equal to A into f of Z. Therefore, Z equal to A into f of Z. I can change the A value here, 1 by A. Therefore, I can change the f of Z equal to K. Actually, A into, I can put 1 by A. Therefore, f of Z equal to K Z. Okay. What about the limit? As it is in B. It is true for in D. At B, what will happen? At B, what about the limit of f of B? F of B tends to KB. Therefore, this is also true here. At K of B, f of B equal to this is true. Therefore, this is true that therefore this function should be like this. Condition on K is mod K should be getting 1. Therefore, the fourth condition is correct. That is why it is not marked right. If this is wrong, this is wrong, this is correct, and this is correct. This is a very good example. Okay. Which of the following true? F is an entire function. Which of the following true? F mod f of z is equal to for z. Okay. Note that it's an entire function. And mod f of z is equal to 1. Therefore, it's a bounded entire function. Bounded entire function means it is a constant. Question is, f dash of x has infinitely many zeros. Is it possible? Question is it possible? That's all. Not true. It can't be everywhere. Okay. Is it true for everywhere? If f is a constant, if it is a zero function, what will happen? F is a constant function. F is identically 0. Every point is 0. If it is a not zero constant function, means it is wrong. Okay. Is there any one function? It is true for at least one function. For one function, then f is a zero function. Is f is onto f of cos z is onto? It is a composition function. F is an onto function from complex plane to complex plane. Cos z is a function. Cos z is a function, and then f is a composite function. Cos z is an entire function. Taking entire plane to entire plane is an onto function. Cos z is also onto function. Cos z is also onto function. F is also onto function. It is a composition of two onto functions. Composition of two onto function is onto function. Therefore, this is onto. This is correct. What about the third one? F is onto. Is it onto? Note that e power z is not onto. E power z is not onto. 0 is not there. 0 cannot be written in e power z. E power z takes everything except the 0. So at 0 is omitted. So if I consider f is equal to identity function, f of z equal to 0, is it? Then f of e power z is e power z. That is not onto function. Therefore, this function is not onto, is wrong. There may be some function onto, but this is not true for every f. Okay. So there are some functions for which this is, therefore this is not true. If f is 1 to 1, this is this 1 to 1 function? Z square plus z plus 2? No. this secondary function, it has two roots. Two roots are distinct, or at least I can find two values such that these 2 points are taken. There are two different roots are there. So there are 2 points where z square plus z2 equal to 2. So for those 2 points, value is 0. Apply f there. So f of these 2 points is 0. Therefore, the function is not 1, 1. Okay. The onto is correct for every f. The first one is correct only when f is an identity function. This is not true for all f. There are some functions where f. This is not true. Okay. The function anti-function defined on the open disk. Okay. So I have not completed that problem. Okay. So I have not written this problem completely. So I omit it. Next problem. Can you hear now? Is it audible? Hello? Is it audible?
Yes, sir. Yes, sir. Audible, sir. Audible,
Hello?
sir. Yes, sir. It is audible, sir. Yes, sir. Audible, sir.
Okay, okay. Maximum principle. If f of z is a non-constant analytic function in region, then f has no maximum. Region means open connected set. F of z has no maximum in D. In other words, given a point z not in D, I know what f of z, modulus is omitted. Add the modulus. I know modulus f of z not. There is some more point which takes modulus more than that. So this is not maximum. Something is bigger than that. Something is bigger than that. Something bigger is there. Something bigger is there. At no point mod f of z has maximum. Okay. This is also I have right here. This is something wrong. Modulus f of z. Okay. Maximum modulus or modulus f of z. Similarly, here is modulus omitted. Mod f of z not less than or equal to this. This is a very good theorem, but I am not going to prove it now. If time permits, we will prove it in the next class. Okay. We assume that. But if it's a closed domain, what will happen? D is bounded domain, bounded, most important. K is closure. F of z is continuous on this analytic inside this. Then it assumes a maximum value because K is closed and D is bounded. K is a bounded closed set. Bounded closed set is a compact set. Continuous function on a compact set must attain modulus value, attain the maximum value. So I get the modulus maximum. So attains the maximum. Where it will attain the maximum? It will attain the maximum only in the boundary, not in the interior. If it attains the interior, it is a constant function. So it attains the maximum value only at the boundary. This result, okay, this is we assume that bounded. Because of the bounded, K is a compact set. Closure is a compact set. If it is unbounded, K is not a compact set. Therefore, this result is true only when it is bounded. It is not true for unbounded region. Okay. For example, I can take the function e power z. F is e power z. My region is on the first quadrant and the second, fourth quadrant. For all points, for the real part is greater than 0. Real part, yes, real part is greater than 0. Then the function is not bounded. On the boundary, what is the boundary? Boundary is the imaginary part. Imaginary line. Purely imaginary line value is 1. For all the values, modulus is greater than 1. So this theorem is not true there. Okay. F of z is analytic. Okay. F of z is analytic function in region which contains a circle, a disk, and also boundary. Okay. On the boundary, modulus f of z is greater than some m. Okay. But f of 0 is a center. Value is small m. Prove that it has at least 1 0. At least 1 0. Okay. Suppose the function has no 0. Okay. Suppose a function has no 0. Then 1 by f of z is analytic. F is analytic. I can find 1 by f of z analytic function. Because assuming that there is no 0, I get 1 by f of z. What is 1 by f of z? F of z is greater than m. Therefore, 1 by f of z is less than 1 by m. F of 0 is less than m. Therefore, 1 by f of z is greater than 1 by m. Here on the boundary value is less than 1 by n. Inside the value is greater than 1 by n. So interior I get a bigger value than the big value in the boundary. The maximum value should be obtained only on the boundary. But a boundary value, no value in the maximum, but the interior value is maximum, means it's a contradiction. Therefore, it has at least 1 0 using the maximum modulus theorem. I have not written the answer. Answer is yes. We have to prove that there is at least 1 0, assuming at least one zero. Assume that there is no zero. Then 1 by f of z is analytic. And this 1 by f of z equal to less than 1, less than m on the boundary, greater than 1 on the interior. So interior value is maximum than the boundary value, which is the contradiction. Therefore, it should attain the maximum. Find the maximum modulus value for f of z equal to 2 plus I in the disk less than equal to 2. Center 0 and modulus less than equal to 2. Okay. The function is 2z plus 5i. Where it attains the maximum? The maximum is certain, modulus maximum is certain only on the boundary. The boundary is mod is, this is not a constant function, only on the boundary. Mod is equal to. So what is the maximum value on the boundary? F of z is attained only on the circle. On z mod f of z equal to f of z 2z plus I less than 2 into mod z plus 5. Z value is mod z equal to 2. Therefore, substituting that is less than 9. So maximum value, something which is less than equal to 9. Can it be 9? That's the question is, can it be 9? If it is 9, what will happen? If this value equal to this, maximum value equal to 9, what will happen? If the maximum value equal to 9 means what will happen? This should be equal and this should be equal. If this is less than, maximum value cannot be equal to 9. If this is strictly less than, then maximum value cannot be equal. So maximum value is 9 only when all these things are equal. 2z plus 5i equal to 2z plus 5 equal to 9. Here mod a plus b is less than equal to mod a plus mod b. And what is the condition for mod a plus b equal to mod a plus mod b? We know mod a plus b less than equal to mod a plus mod b less than equal to. Suppose it is equal. Mod a plus b equal to mod a plus mod b. What will happen? What is the condition? Then origin is there. What is one point? A is 2z. What is b? B is 5z. This a and b should be on the same line from origin. The right ray. Starting from the origin, 5i is known point. From 0 to 5i, join the line, extend the ray. Ray passing through 0 and 5i. The 2z should be on this. If 2z belongs to the ray, then only a plus b, mod a plus b equal to mod a plus mod b. So this equal only when, okay, this only when the 5i and 2z have the same argument, amplitude is same. But I know what is 5i, what is angle, pi by 2. 5i, argument of that is pi by 2. Therefore, this should have a pi by 2. So 2z equal to mod 2z into angle is 2 by 2 e power I by 2. So 2z should be equal to mod 2z e power minus 2 by 2. Okay? But also given us a z equal to 2. Z equal to 2 means what will happen? Mod z equal to 2. So what about what is z equal to? What is 2z? 2z equal to 4 into, okay, e power I equal to 4i. Okay, 2z equal to this. What is mod? Mod 2z. Mod z equal to 2. Therefore, mod 2z is 4. So 2z equal to 4 into e power I 2 pi. E power I 2 pi is I. Therefore, 4 into 4i. So 2z equal to 4i. What is z? Z equal to 2i. So z equal to 2i. So this is maximum value is attained only when z equal to 2i. Maximum value attained on the circle only when z equal to I. So maximum value is 9. What is the second problem? Second problem, f of z, circle is unit circle. So f of z is mod 2z, is less than equal to 2 into, less than equal to 2 into mod z square plus 1. This is less than equal to what will happen? Mod z is 1, therefore this is equal to 3. Therefore this value is equal to 3. This is equal. This is equal to 3. If these are equal, means this is equal. That is 2z square and 1 plus minus 1 should also be the same line. That is argument of that equal to pi. Argument of that. Therefore, z equal to I or minus, because z square is e power I pi. Therefore, z equal to I and minus I. These are the two values. Okay. So we have found out the values here. Is the attained one z equal to something, z equal to I or minus I. Next problem, given n points z1, z2 on the unit circle. Draw a circle, unit circle with the center 0 and radius 1. On this circle, just mark n points. Any n points. Correct? Now, on the circle, there is a point. Mark any point. Okay, that may be Z1 or something else. Join Z and Z1, find the distance. Join Z and Z2, find the distance. Find Z and Z3, join. So Z1, Z2, Zn on the circle. Z is another point. Z and Z1 distance, Z and Z2 distance, Z and Z3 distance, Z and Z4 distance. What about the product of the distances? Product mod Z minus Z1 into mod Z minus Z2, mod Z minus Z1. What about the product? Product should be getting equal to 1 for some suitable point. Okay. That is, these points are given, arbitrarily given. N points are given. They may be very near on the circle, or they may be diametrically opposite, like that. Anywhere given, I can find Z such that the distance between Z and Z1, Z and Z2, Z and Zn, product distance is greater than 1. I can find it. Simple proof. What is the function here given? Modulus. I have to take this modulus of the function. I have to take this modulus of the function. Modulus is already given. So I take f of Z equal to product of Z minus Zi. What about the modulus? What about the modulus? Is modulus of this. Modulus of the product is product of the modulus. So mod f of Z equal to product of mod Z minus Zi. This is the modulus. Okay. What about Z equal to 0? When Z equal to 0, what will happen? Modulus value. When Z equal to 0, this is mod Zi. Mod Z1 into mod Z2 into mod Zn. But Z1, Z2, Zn are on the unit circle. So mod Z1 is 1, mod Z2 is 1. Therefore, product mod Z1 into mod Z2, mod Zn is 1. So the value f of 0 is mod f of 0 is 1. At this function is a polynomial. This nth degree polynomial. F of Z equal to product of Z minus Z1 into Z minus Z2 is a n bracket, linear factors n bracket. Therefore, it's a polynomial. It's not a constant polynomial. Okay. But the interior value is 1, f of 0. It assumes mod f of 0 is 1. But therefore, 1 cannot be the maximum value for mod because it is interior. Maximum value will be only in the boundary. So it attains a boundary value, maximum value is boundary. That value should be greater than the interior value. So that maximum is getting to 1. So maximum is attained at least 1 point because the circle is a compact set. Maximum value is attained at point. So there is at least 1 point for which mod f of Z is, that is mod f of Z is greater than 1. So once again, if we mark Z1, Z2, Zn n points of the circle, I can find a suitable point Z on the circle such that the product distance Z minus Z1 into Z minus Z2 product distance is greater than 1. For that, just consider this function f of Z equal to this. Then modulus is an entire function because polynomial, the entire function, it is analytic inside the circle. Therefore, what about modulus? Modulus is, this is the modulus. I want to prove that it's greater than 1 on the circle, but at center value is 1. So therefore, this value cannot be the maximum modulus. So maximum modulus should be greater than 1. So maximum modulus attained on the boundary. So there is a point at the boundaries of the unit circle satisfying this property. So just using the maximum modulus theorem, we can prove a lot of theorems are there. Okay, I think another theorem is Squart's lemma. There are a lot of questions are asking Squart's lemma. We can take this Squart's lemma in the next session. Okay, in this section we started with Taylor's expansion, Cauchy's inequality. Using Taylor's expansion, we put the uniqueness theorem, and then the maximum modulus theorem, Liouville's theorem. There is definitely one C-part question based on any one of these theorems: uniqueness theorem, Liouville's theorem, or maximum modulus theorem. One question and 1 or 2 questions in the B part. Okay. Similarly, there will be one question in the Squart's lemma and the application of Squart's lemma. We can take it. We want more time to spend it. We can take it in the next class. Okay. Can we stop with this? Hello? Hello?
Yes, sir. Hello. Sir?
Hello, Professor?
Yes, sir.
Can you hear me?
Yes, sir. Yes, sir. Audible,
Hello,
sir.
Professor?
Sir, audible, sir.
Huh? Video conference. Conference. Hello?
Sir, audible, sir. Yes, sir.
Can you hear me?
Yes, sir. Yes, sir. We can hear, sir.
Can you hear me?
Yes, sir.
Okay. I can take the rest one in the next class.
Okay, sir. Okay, sir. Thank you,
Because
sir.
fast lemma, I need at least half an hour time.
Okay, sir. Thank you, sir.
Okay. Okay.
Sir. Thank you, sir.
Thank you. Thank you very much. Thank you.
Thank you, sir.
Thank you. Thank you to all. Okay. Thank you, boss. Oh, thank you so much.
All of you could be here.
On behalf of PG and Research Department of Mathematics, DG Vaishnav College,
Continue.
thank you, sir, for spending valuable time in our T4 session. Really, it is a wonderful session to all our students, research scholars, and teachers. And also thanks to Professor R. Venkatramanan, Head PG and Research Department of Mathematics, for organizing this C4 workshop. I am very proud to inform about our next webinar titled General Measure and Integration. Resource person Dr. Sri Ilango, Associate Professor, Research Department of Mathematical Sciences, Cardamom Planters Association College, 10, will be held on 31st October at 10:30 a.m. Our next session, C4 session, is 31st October at 6 p.m. Thank you.